Good evening and welcome back to Vegas October 1 Sounds. I'm on a roll tonight. I've already covered LRAD, I've already covered speaker systems, and now I'm going to cover gunshot acoustics in 20 minutes or less. And actually, you know me, that's not true. It's going to take me an hour. But anyway, rather than focusing on the complicated aspects, let's focus on the simple aspects. Let's focus on the very basic fundamentals, and let's focus on things which we can put our hands on and know they're true and use them to understand why most of the stuff out there on the gunshot sounds, besides a few creators, is crap. Total crap. Let's start with the most fundamental basics. If I have a source of sound, and we're going to go with that spherical model, anywhere, let's just put it anywhere, and we know the speed of sound, which we kind of do because we kind of know the temperature, but let's just assume for all our calculations that the speed of sound is 1,000 feet per second. So it's the symbol C naught I tend to use for the speed of sound. I'm just going to call it 1,000 feet per second. Okay, I think you've seen that enough to know what I'm talking about. So in 1 second, sound travels 1,000 feet. So if I have a source of the sound here at point A and somewhere else located 1,000 feet away, I have a tape device. It takes this is 1,000 feet. Let's just shorten it up by 1K. Then it takes 1 second for the sound to travel or propagate from point A to point B. And it doesn't matter where that point is, as long as it's 1,000 feet away. Now, if either one of those points, A or B, changes, then that time changes. And it changes, for our calculations here, about for every foot shortened, it shortens the time it takes to travel by 1 millisecond, 1,000th of a second. So if we shorten this distance to 500 feet, then it takes half a second. So that's simple enough, and that's the fundamental thing we're going to talk about now, muzzle blast, because muzzle blasts follow that model. They're very simple. You change the path length, you change the time it takes to hear the sound. So let's come up with some examples. So let's put a shooter on the ground. Let's put a shooter on the ground at point A. Shooter on the ground, and out here at point B, also at ground level, 1,000 foot away, we're going to put a tape recording device, and that shooter on the ground fires around, and that sound propagates out there, and in 1 second it gets recorded on the thing. And he fires the next round, and it takes another second to get out there. The third round, it takes another second to get out there, but the time between rounds is preserved, because the distance between them doesn't change. Nothing changes between them. If that sniper or shooter moves to point C over here, and that's an additional 200 feet, then the sound goes from 1 second to 1.2 seconds. So every time a shooter moves or the recorder moves, then the sound propagation length changes. Very simple stuff. So if I fire 100 rounds from point A, and it doesn't matter which way the bullet goes because we're just talking about muzzle blast, then I'm going to hear those 100 rounds at point B, and it's always going to be the case, as long as neither point A or point B is moving or the temperature doesn't change, that it's going to take precisely 1,000 milliseconds or 1 second for each sound to travel from point A to point B. And if I'm firing them at 10 a second, then there's going to be a 1/10 of a second between each sound. But the time of arrival is still 1 second after the sound was initiated. Time of arrival. That's what we want to talk about. Time of arrival. Time of arrival, TOA we call it. Time of arrival of the muzzle blast. Now, if I've got a shooter that is up straight up above point A, and we'll put this again as point C, and it's 300 foot above point A, then the sound propagates from point C to point B. Okay, and that path is longer than 1,000 feet. In fact, we can calculate it as 1k squared plus 300 squared, 300 squared, squared, square rooted, and that would be the path, which if I pop up my little trusty dusty calculator here and I go gotta change it to pointer, 1, 2, 3 times 1, 2, 3 equals 1,000,000, and then we go 300 times 300 equals, it's too late night for me to do this in my head, 90,000, and then we add the million to it, and then we do the square root, then we'll have 1,044 feet. Alright, so not a big difference, but 1,044 feet. Okay, so in that case it's going to take the time of arrival of that sound from point C to point B is 1.044 seconds, or 44 milliseconds a second longer than the time of arrival there. So if both C and A fire around at the same time, then the sound from point A gets there at 1 second, and the sound from point C gets there at 1.044 milliseconds. Now, if you can measure that time of arrival, then it's plain, clear, and simple that there are two different shooters. And so it's fundamentally trivial if you could measure the time of arrival. The problem comes is that we don't know when the bullets were fired, and that's where all the complexity comes in. But fundamentally, all we're doing through all these complicated algorithms is trying to determine the time of arrival. So if I've got a gunship somewhere in the air and it's moving, then that time of arrival is changing from round to round. Now, it's really hard to detect that with one listening device or one recording, but for every recording device that we add, it becomes more and more complex or harder to not detect that movement. And that's what I do, is I take 10 or 20 different videos located at vast distances or different distances across the venue, and they form these little networks or large networks of paths, and any movement at all in either the shooting location or the recording location becomes apparent immediately, and I can tell down to just a few feet that something has moved. But because I don't know the initial time, I can't tell you down to a few feet where the shooter location is. I can tell you they're different. I can tell you they're different by 2, 3, 4, 5, 10, 20, 30, 100 feet, but I can't tell you the precise location. And so when somebody comes along and says, hey, there's a shooter on the ground, and I go to my database and I pull up all the muzzle blast timings for 20 videos for 3 volleys, including the one that we're talking about, and they're all perfectly aligned and all the times of arrivals are the same, then I say bullshit. And so it's up to the people who are claiming these theories to provide these times of arrival. I've measured them. I'm continually measuring them. I'm measuring them in 5 different ways. And I've been presenting this information. I'm going to continue to present the information, but fundamentally it's a very simple concept. And so every time somebody says there's a shooter at the Luxor, or there's a gunship, or there's a shooter on the ground, or there's a shooter on the venue, I pull out my database, I pull out those 20 or 30 known muzzle locations, and I say, bullshit. Now, people don't want to really believe that I've done that. What they want to do is come up with their own pet little theory and present no evidence whatsoever, no time of arrivals whatsoever, no calculations based on the speed of sound, and say, oh yeah, I saw somebody move their head, or I saw a gunship flying, or na-na-na-na-na-na, or it's an LRAD device, and it's just not true. That's what this channel is all about, doing the hard work, providing the results, and showing you why the rest of the stuff is just total crap. And this is the fundamental basis of all the calculations. Now, deep inside there's complex math because we don't know that initial time at which the bullets were fired. And that's all it amounts to. Everything I do is simply trying to estimate or guess that initial time at which the bullets were fired. It's nothing more complex than that. And I could go on and on and on here about how if you have two positions, you can determine whether it's east, west, north, or south of the first location, or how which time of arrival was recorded first, second, or third, and all that sort of stuff. But you don't need to. You just have to understand this simple concept that when the path changes, the time of arrival changes. And that's really all that I'm trying to say in all this work throughout the entire channel. So, what do we need to explain to create confidence and belief that it is fundamentally that straightforward? Just do the work. And if somebody doesn't really want to believe that the work is being done, and I show my work every time, I'll share the entire database that I have. It'll be in the format that I use because I have written custom software. But I'll share the entire database. And everybody can have 7,000 muzzle blasts timings relative to the start of the videos that they were recorded in. No big deal. So, let's move on a little bit. Let's talk about this. So, we know that it's just a simple matter of measuring the times of arrival. And we can tell that the difference between a shooter on the ground and a shooter at an elevated position, or a shooter at a further distance, because the path length is different, and therefore the time of arrival is different. And now these are just muzzle blasts. I'm not going to get into supersonic cracks. That's a whole can of worms. These are the simple concepts. Alright, so what other theories have we heard? That there were multiple shooters? Well, let's talk about that in a way that might be possible, but which clearly, from my research, is not happening. What are the limitations of this simple concept? Why does it get complex so quick? Because it does. It does get complex quick. Well, if we have a point A and a point B, and they're 1,000 feet apart, and we measure a time of arrival, and the time of arrival is 1 second, there are many points out there that satisfy that condition. And that's the problem, is we're working backwards rather than forwards because we don't know when the shot was fired. So if we have a time of arrival of 1 second, what can we say? All we can say is that there was something 1,000 feet away that fired a round. Well, so if our recording is, let's make it green, let's go back to green, I like green, is here, and the time of arrival is 1 second, and there's 5 different ways to estimate, calculate, or predict that, then we have somebody out here at 1,000 feet. Okay, well, that's a pretty big area. And if you remember the Vera methods, that is precisely what they do. They create this donut or toroid shape in 3 dimensions that says, oh, this is where the shooter might be. And then they use repeated measurements and repeated circles overlapping and find the intersection of those circles to attempt to narrow down the probability of where the shooter is located. So if we have a time of arrival of 1 second, then we know there is a shooter somewhere out there 1,000 feet away. Now that's a sphere. Anywhere on the surface of that sphere satisfies that equation. Okay? And so you'll see that when we're working backwards and we don't know the initial time, then we have to make a family of solutions, and that family of solutions is represented by the sphere of the surface of the sphere. It's still the same simple concept. What is the time of arrival? 1 second. Okay? Now, that's with one observer. If we have 2 observers, This time I'll put the second one in yellow. Okay. And that observer records a time of arrival of half a second, or 0.5 seconds, because it's closer. Then he's got a circle, he, she, it, or whatever, that's smaller than that one. And where they intersect, those two spheres, or in two dimensions, the two circles, represents the probable location of the shooter. It's that simple. Two spheres. It's a Venn diagram. Where they intersect, the overlapping regions, is where the shooter is likely to be located. And you see, so if we add another observer somewhere, and we have a time of arrival of let's say smaller this time. Let's say about 0.3. Then where they overlap, it is potentially the position of the shooter. Now, this example isn't real because I don't really think that there's a real geometric situation that would satisfy all three of those equations, but it is conceptually correct. So that's what we're trying to do now. That's with intersecting spheres. Okay? Another method says that, and all we're doing is using time of arrival. But because we don't know the initial time, we have to make all these intersecting diagrams. You'll recall that I said that if you have two observations, point A and point B, and you synchronize the videos together so that you can get an estimate of the time of arrival, and you find that point A, the time of arrival is 0.1, and point B it's 0.4, then you can draw a line between those things, bisect it down the middle, and since the sound arrived at A before it arrived at B, then it has to be somewhere over in this direction. Okay, and then you can take a second set of observations and do the same thing. Two observations. In this case, let's say this one was 0.3 and this one was 0.7 times of arrival. You draw a line between them, bisect it, and since this point up on the top was first, then everything up that way and where they intersect is the likely location for the source of the sound. That's one method. Another method, again, it's the same simple concept though. Take the time of arrival or the time delta, whichever measurement you can get a hold of, and then using multiple observations continually refine where the shooter is. In the Vera system, it's the same exact concept. Nothing more complicated, nothing less complicated. It's just that which method you choose has a different set of equations, and solving those equations can be complex. So in another Vera system, and for those that don't know, Vera is the Carnegie Mellon student system that they put together that's online. You can use it. You can upload the videos and select the points, and it'll go off and make these graphs for you. So in another Vera system, they use two observations again. Oops. Two observations separated by a distance of, if the time between the times of arrivals for each point, if we measure the difference, then then call it delta t and multiply by the speed of sound. Okay, then that's the distance between those 2 points. And then we can, through an equation, calculate the point at which hyperbolas cross, and everywhere on those lines drawn is where the shooting location is, given the distance between the observations and the times of arrivals, or the deltas between the times of arrivals. And so once again, if we know which side came first. If this side recorded it first, then we can eliminate this curve and just go with that one. And by repeated application of that, and in 3 dimensions, these are oh god, I forget the term, but basically, it's like the cone, the nose cone on a jet plane. It's that shape. And so if we take multiple pairs of observations, we can have all of those cones intersect, and where they intersect becomes the more probable location for the shooter. So all of these things are based upon estimates of that simple concept, the time of arrival. And every theory must come to grips with that concept. It doesn't matter whether it's the helicopter. It doesn't matter whether you believe it's from room 134. It doesn't matter whether you believe it's on the ground, the other side of the venue, fake, from the speakers or from LRADs, which I just addressed. It all has to obey the known concepts and precepts of acoustics and gunshot acoustics. And that's all this channel addresses, is those concepts. So before I get off too far from it, I just want to make it very, very simple. That's all this is doing. And so when you have all 1,000 or more of the shots laid out, you've measured their locations in each of the videos, and you've come up with an estimate of the times of arrivals, then you can do a lot of wonderful magic. But you can't do it when you make one observation in one video. You can't do it just by making no observations and observing some flashes in the sky. It just doesn't work that way. Life doesn't work that way. You can't pretend you have a set of brakes on your car and stop when in fact there's nothing there. It just doesn't work that way. Okay. Well, anyway, I think that's all I really wanted to say, is that this really is fundamentally a simple concept that you're trying to get a handle on, that time of arrival, leastways for the muzzle blasts. And there's multiple ways of doing it, but they're all doing the same thing, is they're all solving for where the original point of the source of sound is via intersecting or overlapping equations or graphs or three-dimensional objects. It's not fundamentally complex concept, but to implement it does become very complex very quick. And during that complex stuff, you have to be extremely aware of the margin of error in your calculations. Okay, I'm going to wrap it up. That's the third one for tonight. It's enough, going off and hyperventilating on this stuff. But I think I've given you 3 videos which show you 3 simple things that give you a big handle on recognizing when, 1, somebody's not giving you enough information, 2, when somebody's BSing you, and 3, what's possible and what's not possible. All right. Have a good evening, and we'll see you in a day or 2.